What am I doing? Let's get it, baby. Isomorphic strings. What the hell does that mean? Isomorphic strings. All right. LinkedIn, Amazon, Adobe. Crazy. Given two strings, S and T, determine if they are isomorphic. Two strings, S and T, are isomorphic if all the characters in S can be replaced. Oh, wait. If the characters in S can be replaced to get T, all occurrences of a character must be replaced by another character while preserving the order of characters. No two characters may map to the same character, but a character may map to itself. Two strings, S and T, are isomorphic if the characters in S can be replaced to get T. So egg you can replace the E, G, and G to get A, D, and D. You can replace F. Okay, so the O can be replaced for the A. So that's what when it said that, but no two characters. It said all occurrences of a character must be replaced by another character while preserving the order of characters. No two characters may map to the same character, but a character may map to itself. So A and R both can't map to O, but an O can map to itself, I guess. Let's take a look at paper. So P can map to T and T, while A maps to I, and E maps to L, and R maps to E. Okay. I kind of need more test cases though. As an engineer, you come up with test cases, right? So let's. So these are all obviously the same length. So here it'll be the same length. Okay, so no need to check for that. We had a problem before. We had to check the length of strings. Okay, well let's freaking. My hands are greasy. What the fuck? I just took a shower, so I'm a little bit lotioned up right now. Anyway, huh? Okay, so let's look at egg. And where's my timer? Whoa. All right. So we got egg and we have add. And this is true because E can map to A and G can map to D. So, okay. All occurrences of a character must be replaced by another character while preserving the order of characters. What does that mean? So all occurrences of G must be replaced by another character D while preserving the order of characters. No two strings may map to the same character, but a character may map to itself. No two characters, but no two different characters. So E and G both can't map to A. You can't replace an A with an E or a G. You can't replace E or G with an A. It's either pick A or G, E or G. Okay. So if E maps to A and G maps to D, that is isomorphic. So I need to find a test case where this is like obviously wrong, right? So if you look at foo and bar, we know that F can map to B, and we have an O which needs to map to either A or R, but not both. And so because of that, so how do we come up with how do we come up with the answer? Because it's saying true, false is a Boolean, or returning a Boolean. So how do you know that it doesn't? Do you have to actually do the replacement? Probably not. I think that I think if we take a look at each character in S, we give it a key in a dictionary. And then we can just basically iterate over T and say like, okay, you know, I don't know. So if we initialize a mapping with empty strings, right? And for every character we see in S, so for every unique character we see in S, we just give a mapping. And then we say, okay, now iterate over T and add that mapping to just any character. It doesn't matter what character you add it to, right? No, you just have to you're just replacing characters. So if we just say that E is A and we say that G is D, right? That's valid because you map over A and we say, okay, E can be A, then we say G can be D, and we have the other D, and we say, well, D has already been mapped. Okay, so I'm looking at a dictionary for mappings and maybe a scene array, or like we can't look up the values, right? We could say like if this letter is in the values, but that's a little, I don't know. But I mean, okay, that's crude, but okay, whatever. Right, so if let in values, right? In the dictionary.values. I'm gonna make a list of it. So basically, that creates our mapping, right? And so in the happy path, this is isomorphic because we never hit a specific case, right? We never said that, we said if a character is not in the values, that means it hasn't been mapped yet and therefore should be added. If a character So for example, if we had, let's say I just changed it to like Aggie, so EGI, we would map an I. What would I map to? I can't map to anything because G and I both can't point to D. Right? You gotta pick one. Is that right? So no two characters, G and I cannot map to the, but E can map to itself. Okay, that's fine. So what does that mean? That means that D is already in the mapping. This is an interesting one. This is a very interesting problem, and it's seen by a couple of companies. Not that I'm interviewing at LinkedIn or Amazon or Adobe, but you know, huh? So what's the case in English, right? Well, the case is that there's no mapping for I. But does that make it not isomorphic? Yeah, because you can't replace there's nothing you can replace the I with that creates add. So therefore it's not isomorphic. Okay. So we'll initialize a dictionary with mappings from S, and we'll initialize it with empty strings. So that's basically like no mapping, right? We iterate over T and we attempt to add in sort of in line, you know, there's another way. I think there's other ways to do it too, but we'll start with this for now. So we initialize it with empty strings. We then say, we then loop over T, iterate over T, we take a look at each character, we try to map it to a character in the dictionary, in D. And we're basically saying, okay, if this letter is not in the values of this dictionary, that means it hasn't been mapped yet. And therefore we should just assign that's weird. Yeah, how do I do that? Can we do that? I'm trying to think of the actual code. How do we actually assign them? Well, we can look through the keys, right? We're iterating over the. I'm trying to think. If they're the same length, we can just zip. Oh, I really want to say zip. Well, there are probably some Pythonic ways to do this, right? I mean, a zip does it basically creates a list of what tuples of two iterables, and it does it to the shortest length of the shortest. So if they're the same length, right? Ideally, if we did a zip on S, if we did make a list of S and T, and did a zip, what would we check for, right? If we zipped S and T, we'd get E, A, G, D, G, D. Or for the incorrect one, we get E, A, we get G, D, and we get I, D. So how do we validate this zip? I'm exploring the zip option. I don't know why I'm exploring this, but we'll see. And so what if we did what's it called? No, you just set? Probably not. I don't know why I keep wanting to do sets. I keep wanting to do sets so bad. Then we'd have to iterate over each tuple to check if it's like valid, I guess. Or we check for basically that the character on the left doesn't map. The character on the left maps the same character. So we can't have G mapping to D and I mapping to D. Correct? That's what we check for. If that's what zip does. Yeah, it creates tuples. T3 onto 3. Okay. I mean, if we zip it, it kind of creates our iterator for us, right? Or not iterator, but it creates our mapping for us. We just do a zip. And we can validate, we just validate the zip. So how do we validate? I kind of like this idea. So how do we validate the zip? Well, we have to see the same pairings. Well, it has to follow some rules, right? What are the rules? The rules are that order matters. Order. I want to see an example for order. Like what do you mean order matters? Right? And then it's like, so O can't map to A and R, is what I'm understanding. I mean, we could keep track of like a scene list. Okay, let's try like a scene list. How do we do that? Well, we keep a list of scene, and we basically just insert things as they've been seen. But if this has been seen before, that means it's if it hasn't been seen before, we have to validate that it does not exist in another form. It doesn't map to anything else. So for example, we'd say EA is a mapping. And if it's not in the list, that's cool. And if our list is not empty, right, then we might already have E mapping to something else down the line. So we want to check, we want to make sure that E is not mapping to anything else. So that every occurrence of E is mapping to an A. I feel like I want to keep that as linear time as possible. But so how do we create that? How do we validate that every E maps to an A? We have to iterate n length, or in the worst case, over the entire list, and basically check to see if the first character is an E, if the first in the tuple is an E, then validate that it's also mapped to an A. And if not, it's not isomorphic. That's basically what we do. So okay, let's code that out entirely. So we're gonna zip. Since they're the same length, the zip will work, right? Since they're the same length, the zip is gonna work. And we're gonna say, so zip, we'll turn them into lists. So we'll do a list of S and a list of T. So we'll get S in a list, gets S, gets what, LST, or in a list of S, and T list gets list of T. And we'll say get our, what is it called? We can call it isozip, I don't know. ST zip gets a zip of S and T list, right? So then it returns back tuples of E. It's an interval of E to A, and then G to D, and then G to D. Okay, which acts sort of as a mapping, and we just need to validate that this mapping is work. We need to validate the mapping basically. So we then say, okay, let's check if this is isomorphic. So you can replace an E with an A, which is cool because we're using our scene list, right? So E and A is fine because our list is empty, so therefore adding this is okay. G and a D, we don't have any G's, so that's another iteration. That's many iterations. Wow, we're doing a lot of validation. That's a lot of revalidating. But let's finish it. There are no tuples with a G, so this is safe to add, right? With this second case, there's a tuple with a G, and we validate that every tuple with a G maps to a D. And because it does, this is also valid to add. If it didn't, then we'd be forced to exit to return false, not isomorphic. Because then an O maps to an A or an R in our second example. The P maps to T's, that's fine. The A maps to an I, L to E. Okay. Does that work? So how do we write the validation code? Well, once we have our zip, then we're basically adding this to scene. And we're essentially saying that one test case is just to say if the list is empty, just add it, which is fine. If list not empty, else we're gonna validate that, and we hit the validate case almost all the time. So let's try a helper function to validate, and it returns back out to the, well, it either returns a Boolean or, that's weird, a Boolean or a list. That's kind of weird. Right? Or maybe we just use validate as a way to validate, right? I mean, validate seems like a function, right? So we'll call it validate. If, you can say like call it valid, we'll say validate mapping. Right, and it takes in the next possible in the list, and it basically does the math of validating. So, okay. So it's our validate mapping code. Our validate mapping code basically checks to see if the map we want to add, it wants to add it, but it can't add it if a character is already mapped to another character. That's basically the only thing we're talking about right now. I don't know about the other one where it says like preserving order, but because the zip keeps our order, so sure. So basically, how do we write that code? Again, I keep going back to it. How do I write that code? So given a tuple and the current list, validate that this is able to be added. So basically we're gonna we're gonna pull the first character out, and we'll say this is an E, and we'll say if, we take a look and say like for each tuple in this list, for each tuple in the list, check to see if there is an E. Since there's not an E, this is already safe to add, so return true, right? And because there never will be an E, that's fine. For the G, there's no other G, so return true. There's another G, right, in our list, then validate that the two that they map to are both D. Then validate that whatever you pull out of here, that they're equal. If they're not equal, return false. What does that code look like exactly? I mean, we're looking at we can look at like left character. I don't know, left's one for recursion. All right, so I'll just say left. Left gets G. We'll say for pair in our scene list. If our left equal the pair left. So if we ever find that it already exists, we want to return false in one case, right? If we have the pairing and the right is not equal to the left, return false. Otherwise, return true. All right, let's do it. So S list gets a list of S. T list gets list of T. Then we say our ST zip, Saint zip, why not? Gets a zip of S list and T list. Then we basically say scene gets an array. Then we say for pair in st zip if we'll call valid mapping, we pass in the pair and the scene array. We'll say if not valid mapping, return false. else return true. Right? Without mapping, we'll give it a pair, which is what? A tuple of something like that, right? If you want to start type checking stuff. Whatever. Not a huge deal, but else scene dot append pair. Oh, oops. Lovely. Our scene code, we get the left, which is our pair at 0, the tuple. Say for a pair in scene. If left equal a pair at 0, and the, I'll call it right, the pair, I say pair, right? I really should say, sorry, this is bad. I'll call it current pair. I mean, this is pair. Pair is fine. And right not equal to, I'm saying pair 1, return false, else return true. I noticed I didn't even run this code through a test case. I mean, I kind of did, but I kind of didn't at the same time. But it passed everything. But it takes too long. Oh. Why did it say true? So if we zip it, right, we get B, we get BB, A, we get B, we get, oh sorry, AA, and we get DB, and we get CA. So it only returned false because where? That's true. That's true. Then we have D and B. That's fine. What? Yeah, why did it return false? Let's see. Print what? Left, right? Left, right. I'll say also say scene. And just submit that again. I should just copy. I should just copy that thing around. I should copy that into a test case. So BADC and Baba. That's crazy, bro. BADC and I returned true. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . What? Okay. How? Wait, this is not valid? What do you mean? Oh, B? No. Oh, I forgot a case. Okay, that's the case I was... Is that... So B maps to B, A maps to A, D maps to B. That's bad. How is that bad? I don't understand. Well, okay, so just like in the egg one, G can't map to multiple things, and vice versa, this can't map to multiple things. So we gotta check both. We gotta check both the left and the right, but they don't have to be equal though. B can't map to B itself, and so where did it return false is my thing, right? Where did it return false? It went into valid mapping. Right? So BB is fine. BB is okay. A is okay. So it thought DB was okay. But that's wrong. Because it's flipped. Oh, because B already maps. Huh. Oh, that's okay, that's interesting. Yeah, because B already maps to something the other way around. So D can't map to B as well. So to solve that directly, we would just check the right one too. Yeah, that seems okay. So basically, say something like if the left and right are not equal, or if the right is in the or we're saying if the right one is in something and the left is not equal to the right one, which is very possible. And then paper doesn't match. P and T, A and I, P and T. So E to L is valid and R to E is valid. Yeah, I don't know. I think I'm off already. I think this problem already was a risk. Or my solution was already a risk. So let's just look at what Lee has to say, because somebody have one. Let's take a look. Okay. Different solutions, similar time and space complexities. That's what I thought. Okay. The discussion section is filled with various tricks to solve the problem. However, we will stick to a couple of approaches that have been optimal time and space complexity and are reasonably easy to come up with during an interview. Regardless of which approach we use, three conditions must be met for the two strings of isomorphic. We can map a character only to itself or to one other character. No two characters should map to the same character. Replacing each character in string S with character. Replacing each character in string S with the character it is mapped to results in string T. Okay. Matching the order will be easy since we will iterate over the two strings and do some sort of comparison from left to right. The task of ensuring that the character order is the same in both strings will take care of itself. Next, we need to somehow maintain a mapping of characters, hint dictionary, or come up with a way to convert both strings into a common format, like integer assignment to characters, and then check if the converted strings are the same. These are two solutions that we'll explore. Again, many other tricks can be used to solve this problem, and thus there are a variety of different solutions. A compilation of other found here, which is the discussion piece, but they'll be difficult to come up with an interview. Okay. Character mapping with dictionary. So, intuition. First solution is based on the approach indicated in the problem statement itself. We will process both of the strings from left to right. At each step, we take one character at a time with the two strings and compare them. There are three cases we need to handle here. If the character does not have a mapping, we add one to the dictionary and move on. So P and T, P maps to T. That's what I thought of doing, but I was doing like two separate loops. It's weird. The characters already have a mapping in the dictionary. If that is the case, then we are good to go. So P and T already has a mapping. Sweet. The final case, and they use the one that tripped me up. Wow, that's crazy. Is when a mapping already exists for one of the characters, but it doesn't map to the other character at hand. In this case, we can definitely conclude that the given strings are not isomorphic. So B already maps to B, but D cannot also map to D. No two characters can map to the same. Now this fails under our first case because D doesn't have a mapping in the dictionary. We'll add the mapping and move on to the next character. However, this is wrong. The character B in the second string already has a mapping. We need another dictionary. When a single dictionary implementation breaks. What? We will need two dictionaries instead of one, since we need one-to-one mapping and vice versa. Since we need one mapping from the S to T and vice versa. Let's look at the algorithm to see modified cases. So we define a dictionary mapping ST, which we'll use to map characters S to the characters in T, and one from T to S. Next, we iterate over the two strings at the same time. Let's assume the character in the first string is C1 and the second character is C2. If C1 does not have a mapping in S to T and C2 does not have a mapping in T to S, we add corresponding mappings to both dictionaries. At this point, we expect both the character mappings to exist in the dictionaries and their values should be STC1 equal to S2. Okay. If either of these conditions fails, C1 is not in the dictionary C2. If either of these conditions fails, C1 is not in the dictionary, C2 is not in the dictionary, or unexpected mapping, we return false. Return true once both strings have been exhausted. Okay, so the second case is if C1 not in, which I was doing something similar. I was doing a comparison, but a dictionary I think makes more sense here. I like this one. I like the one a lot. What? 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 Okay, I like this one. So you take two mappings, you say if C1 is not in S to T and C2 is not in T to S, then you create the link through two. Then it says else if mapping ST that gets C1 is not equal to mapping. So that means that C1 and C2 are already in the mapping. Both are not in it, which means that at least one of them already is mapped, C1 or C2, in S to T or T to S. Then we have to validate that they're the same. If they're already in there and they're the same, we're good. If they're both in there and not the same, we're bad. It's bad. Return false. This one's kind of weird. So there saying that an index mapping and a new string. For I and C and S, if C not an index mapping and C gets I, gets an index. New string dot append the string of the index. Oh, okay. What? Wait, what? So the string as an input and returns a new string with modifications explained in the original. Store the character index mapping. What? Wait, okay, hold on. I gotta read this. This is weird as fuck. Zero 1 0 3 4. Character P, character index 0. Set of graphics and logarithms x XOX, both transform to 1 2 3 4 5 6 7 8 9. 1 2 3 4 5 6 7 8 9 1 1 0. Yet they are not isomorphic. So what went wrong? Well, the first 10 digits are unique and the same is true for 60 bits up to. However, 11th and 12th characters map 11 and 0, while to avoid confusing 11 0 and 110, we can add a delimiter to help differentiate. We then see that, oh, so XOX and there's ICS. So they're creating a mapping using the index, and they're basically saying that, so for example, in foobar, F would get what, 0, and B could also get 0. O would get 1, and A would get 1. O would get 1, but then R would be 2. So they're comparing the equality of their mapping. So that's how the order is also maintained, kind of. So okay, I get that. So an example of foobar, the number would be 011 Y. The number for foo would be 011 because F is at 0, and then 00 maps to the same index, 1. But bar, that means that they can't map to each other because O would have to map to 2 different characters, and that's interesting. So it's a way to either transform them, which is O of N. This one is O of N, O of 1, because we know how many characters we can store. Wow. Okay. I like this solution. It's fun. Very, very fun. The other one's kind of cool too. I'm not gonna lie to you. I will definitely upvote this problem. Super duper fun. Anyway. Cool. Hash table. Anyway. That's crazy. Okay. So my one string problem is done. I did say I was going to go over the ones I solved this week. and at least trying to figure that part out. So I'm just do that now. I'm gonna briefly just go over each one just to like refresh myself on how they were solved. Okay. As time goes on, like the frequency is different. Almost, I think it's also related by some of those solved. So, but anyway, Roman to integer. So I don't think I solved this one on my own, right? I didn't. But okay. So basically, in this problem, we have a mapping of Roman to int, and we're essentially checking for a couple cases. So we're iterating over S, trying to return the right sum, basically. And so we're basically gonna just add. I modified the problem a little bit, but the solution a little bit, but we're basically gonna create a sum, a total, based on the characters in S as they map to Roman integers in this mapping. And so we basically gonna just add everything together until the character, because they should work in descending order. But there are three cases, actually really 6 cases, where there's a character smaller before a character that's bigger. And in that case, we want to do subtraction. So basically, we're just adding and then doing subtraction in that case, and that's pretty much that problem. That's problem list all. Oh, this is order of problems. I don't want to do that. I want to do this. All right, let's look at valid parentheses. This one I think I solved on my own without help. So they had a different solution where they actually mapped the closing brackets to open brackets, where I mapped the open brackets to closing brackets. And essentially the thought process here is that you keep a running tab of how many of the open parentheses in a stack. And basically for the string to be valid, you need to validate that after you've seen all your open brackets, that any closing brackets are closing the right parenthesis. That's basically what to do. But you use a stack to keep track of the relevant open parentheses. That's basically what we're doing. So it's not very complicated. It's just something that if you don't know, so using lists for like recency tracking or backtracking, and then we're looking. I wouldn't say backtracking, but dictionaries are definitely like common, like mappings of types, and then iterating over the string is also common, checking for certain conditions. Let's take a look at the next one, which is FizzBuzz, another fun one that everyone gets to have. So ways to improve FizzBuzz. Basically, you would create a mapping of like divisors. So I actually want to bring in the better solution here, because let's say you want to add like n length divisors, you'd have to iterate over the divisors and basically say, if this number is divisible by all of them, then just like append them as they go. Otherwise, return the int. So if you look at the solution real quick, let me try to modify it here without looking at it. So, well, we can't do that here actually. You can kind of call it yourself, but you get a bunch of divisors, and you iterate over the divisors, and you say, okay, your array builds out. Let me look at the solution because I'm gonna butcher the explanation. So if you want to, it's string concatenation. There's one more. You have a list of divisors. And you essentially said that, okay, we want to consider 3 and 5 as a mapping of divisors to the string you add. And so you loop over 1 to n, and you essentially say that for each key in the divisors, now why is this O of n? This is O of n? Well, the divisors is not always, I guess, n length. Well, how many divisors do you have? It's not n squared. Well, if it's divisible, append the string. And then if everything got divided, then just append this and then add that to your answer. So it's not very complicated, but it's helping with like growing the problem out to handle like all kinds of cases, right? That's a software design thought process to have. Oh, it's crazy. Cool. I want to add that deposit because that one's the one you want to like going to get to eventually. I like that. I like the answer a lot. I'll submit that as one of the ones I submit. This is a good answer to have in your back pocket. Let me respond to my girlfriend's text real quick. Hold on, she's talking about all the food she ate. Where's that mouth-watering emoji? Anyway, cool. Back to our. All right, longest common prefix. Another video that I think I did pretty well on. Did I? Yeah, I did. Was this solution good? Anyway, longest common prefix. So this is about getting the string with the longest common prefix between two words, two other strings, or actually it's a list of strings. Oops. And so basically we grab the shortest word because that is the length of the longest prefix if all the letters in that word are valid as a prefix. So we never want to go past that. And we basically say, okay, for each for each letter in the shortest word, right? For each letter in the shortest word, check that it is it's the first letter. What am I saying? Take a look at each letter in the shortest word and validate that it's across it. So for example, it basically runs anyway, and the response can be an empty string, or it will be, yeah. So if not string at I at pointer. So this is iterating over each word, and basically we're basically taking the current. So for example, in this example, right, let's just use an example because wow, that explanation was terrible. So flow is our shortest word. So FLWO, which is what this while loop is going to iterate over. It's going to iterate over FLWO. And we'll say for each word in the list, if string at I, so let's say for example that's flower, if the current if the letter at the pointer index is not equal to the next, right? So when I'm to the same thing of the next word, then return out. For each, so basically we're saying if f of flower is equal to f of flow, and if f of flow is equal to f of flight, we're good to go. Add f to the, and then we're saying, okay, if L of flow is equal to L of flower, and then if L of flower, well, that's not the exact order, but you understand the idea, right? That we're basically saying that we're comparing the characters of the shortest word to every other character in the other strings to see if they basically match up. And we're keeping track of the answer, but we're not checking if FL is there. If F is in there, if that doesn't return out, then we know that F's in and we can just add it. Then we just move on to L, or move on to what's it called? To L, yes. We look at O, but then we compare O of flow to the character, and it's not, so we return FL. Basically, that's the problem. Explain it terribly, but you get the idea. I like that one. It's good. Let me quickly just thumbs that one up. I like that one. Okay. Then we did first unique character in a string. And the best solution to this one was to count, use collections to get a frequency, and then basically look at the index and the character. Let's say if the count is equal to 1, the first unique one is basically that. That's the simplest way to do it. I don't know. Did I submit more than one solution? I didn't. My original solution was a little bit more complicated. I was doing some summing and some weird stuff. I don't know why I didn't think of doing a dictionary, but yeah, makes perfect sense. You also do that yourself. You also using collections is a Pythonic way to do it. You wouldn't want to create your own code for that, but yeah, using what's it called is a good way to do it. The collections I counter, right. And I've seen that around a lot, so that's good to use there. Reverse vowels. That's one I think I got by myself without much help. So I modified it slightly to give us a set. I have a couple of solutions. My first solution that was accepted took a vowels array, similar to the other ones, but just I used an array instead of a set. A set makes more sense, right? It fits better because you're not modifying the vowels array, but who cares really, right? So this is basically saying that if we're iterating over both strings, and we're basically saying that if the character that we're at in both strings is a vowel, we're gonna do a swap. If one's not a vowel, but one is a vowel, we're moving it's two pointer, basically, to do a swap only at two vowels. That's basically what we're saying. That's basically it. My latest solution return was a set using the same logic anyway. So then the response was to join. If we did the swap, then we did it in S list, and we just create a list. We create a string out of S list, and that's it. Next. So lots of turning characters into lists, iterating over strings, creating mappings of strings, lots of frequency counters, right? I didn't do time and space complexity analysis on all these. I need to do that. I'm doing that more often. Practicing what loops and spacing looks like, especially with strings. Is anagram. Anagram means that if you rearrange S, you get T. So we said that if they're not this, it didn't say S and T were the same length. So So I basically said if they're not the same length, it's not a valid anagram, because if I have foo and I have foo bar, I can't rearrange foo bar to get a shorter word. Yes, foo is in there, but it's about rearranging the characters, to get S, rearranging T to get S. So if not the same length, return false. Else, if it's the same length, it can be valid. It could be. So first we gather a frequency of each character from S, and then we look over T and we say basically, if a character is not in the mapping, that means it has an extra character that doesn't even exist. Therefore, we must return false. Or if we've already subtracted all the characters out, we can't have more A's than possible, so just return false there too. That's pretty much that solution there. Time complexity, if I just do it now, O of n. Worst case, we loop over both S and T, but they're not nested, so it'd be 2n, which asymptotically goes to, well, I shouldn't say that. 2n, which simplifies to just n. And then space complexity, technically every character could be unique, but there's only 26 characters in the dictionary, so it's not, well, I shouldn't say it's not constant. I shouldn't say it's constant. Yeah, it could be, it's going to be n space, assuming we, well, it's not infinite, but it's n space. Is that right? I think that's right. Well, you got to know. You kind of have to know, though. You can't just, ask LeetCode. I do want to validate. I think that's right, though. It's n, because it could be, well, no. The keys of our dictionary is 26. So it's technically O of n runtime constant spacetime. Yeah. Yeah. The list can't infinitely grow. It's going to just increment more numbers. So the most we can have is 26 keys, 26 key value pairs, and that's pretty constant to me. Next one. Remove all adjacent duplicates in a string. Another fun problem to solve. So essentially we're saying that this is my solution or no? I did not have a solution. I totally succeeded. My solution was a little bit more. I don't think I had a solution. Did I have a solution? I don't think I did. I think this is one from the discussion board that did not have a proper solution to it, but the one of them did. And so I think output, and then for character in S, if output in, what? If output not empty, and the current character is equal to the last character in output, pop out the stack, I guess. What? Else? Oh. Why are they using -1? I don't understand that. Why they're using -1. There's no LeetCode solution to this problem. I think it's just not. Oh, there is. What? Oh, but the first LeetCode solution, I guess, didn't actually work. It was weird. But the second one, so we're iterating forward. And we're trying to see if it's. Oh, yeah. So I actually ran through this And basically it said if the current character is equal to the last character of the stack. So if we actually run through this solution, which I think is actually kind of cool to see how it works. I need to review this one. This one's a little bit weird, but and it wasn't like a popular one. It's popular, but it wasn't like it's like not recent, I should say. Not a companies that I want to interview at. Basically, it was like, so if you have a stack, right? There's a lot of stuff on this board, but this stack is terrible. This whiteboard is shitty as fuck. Terrible. But anyway, let's say we have a string. We're trying to remove all duplicate. I think it was like A, B, B, A, C, A was one of the ones we had. And so what it does is it says, okay, so it says, is A equal to, so then it compared, what's it called? So it compared S. Oh, it says if output, so no, therefore append A. Then it says if B, well, that's dumb. If B equal to A, no, append B. If B, oh, then pop it. That's weird. Wait, am I doing this right? Am I doing this correctly? Am I doing this properly? I could just run the code with some print statements and get something out of it, but it's 7:45. Is it snowing? I think it's still just foggy, right? It's just really cloudy. It looks like it snowed, but it didn't. Nice. Everything's so white. Um, yeah, so output's empty. So we add A. And then we say B equal to A. No, so add B. And we pop A off. Wait, what? I did it. You know what's funny? If I go back and watch the video that I did, I actually had the same issue. I was like, what am I doing? So output's empty, so append A, right? Then we say B equal to A. No, so append B. B equal to A. So no, append B. A equal to A. That doesn't make any sense. Append off B. I'm not understanding this properly. I gotta run it. I don't know what's going on. I just gotta run it because I have no idea what I'm doing right now. Let's see. Description. Let's print output for each iteration. Let's print output and the character. So A, so A got added, B gets added. We do one last print out. Okay, so because output is empty, we just append A. And since B is not equal to A, we add B. Since B is equal to B, what? -1 is the end of the. Oh, well, yeah, the end of output. Why was I comparing it to S? Why was I comparing it to S? Am I crazy? I think it's exactly what I did last time too. I was like, what am I talking about? Okay, so yeah, there we go. So A is empty, so we add A. B is not equal to A. I keep saying out. It's we're checking if it's the end of output. So because B is not equal to A in the stack, we add B. Is B equal to B in the stack? Yes, take it off. Is A equal to A in the stack? Yes, take it off. Is C there? No. Is A there? No. Okay. That's what, yeah. And I think the same thing happened to me last time. I was like, what the frick am I doing? So yes, interesting solutions to the problem. Hard to come up with, I think, on the fly. It's a little tricky. It's an Amazon and Facebook and Yahoo problem, but it's not super. These are going to get more and more. This is going to get more and more infrequent in terms of easy string problems. So we gotta be careful about that. What else have I solved? And then isomorphic strings as of today. So that's it. Tomorrow we're doing find common characters. No solution to that one though. That'd be fun. But they get increasingly less. I'm basically gonna go until I have like a twitch for string problems. Like I kind of have an idea how to solve it. If I get increasingly more or less common, because you would have seen the majority of each one. Anyway, that's it. We're done. Let's take a break. I am exhausted. It's 7, almost 8 a.m.